Hey everyone, in Chemistry 40 world, it's Dr. Carroll here. We are looking at chemical kinetics, specifically Unit 3 lecture theory. We're going to look at collision theory and reaction mechanisms in all their glory, all the guts about them. We'll look at RPIC diagrams, which are reactants, products, intermediates, and catalysts. We'll look at similarities between intermediates and catalysts. We'll see that you really can't have more than three things smashing together at once. So, get out your booklets, and we're on page 26. And so, what do we have here? Let's say we have a reaction, 2 molecules of nitrogen monoxide smashing into 1 molecule of oxygen to give you 2 molecules of NO2. That's our overall reaction. It might happen in one step. If it did, 3 molecules would have to hit together. Successful 3-particle collisions all at the same time in the right direction with enough energy are quite rare. Right direction? I don't want to say in the right direction. Let's say in the right orientation. I think that's a better word to use. In order for chemical reactions to occur more quickly, reactions tend to occur in steps, just like a DJ would say, break it down into steps. With each step, and I can say that because I am a DJ, with each step involving a 2-body collision, or bimolecular, the chance of a 2-particle collision being successful is much greater than a collision between 3 or more particles. Now, if you do have a reaction and it does take place in just one step, it's called a simple reaction. Most reactions take place in more than one step, and they're called complex reactions. So even if it's just 2 steps, it's called a complex reaction. So experimentally, it is proven that the 2NO plus O2 goes to 2NO2 does not take place in one step, but actually in 2 steps. Both of those steps bimolecular. The first step is that 2 molecules of NO smash together to form an intermediate called N2O2. Intermediates don't usually last very long. Soon thereafter, not necessarily in the next step, but in the step pretty soon after that one, the N2O2 then reacts with something else and is no longer seen. So an intermediate is a creature that you do not put into a reaction. It is created in the reaction, and then later on it is consumed. So in this RPIC chart here, R stands for reactant, P stands for product, I stands for intermediate. Some people call it reactive intermediate. I don't like that because it's confusing between reaction and intermediate. So just call it intermediate. And C, as you might guess, stands for catalyst. And not all reactions have catalysts. This one doesn't. So my reactants are NO, my products, or NO and O2 are my reactants. My products are NO2. My intermediate is N2O2, and I don't have any catalyst in this example. This little asterisk with a circle is a way to write overall reaction, because your steps in your reaction mechanism, your series of steps, have to add together to give you the reaction mechanism. Sorry, to give you the overreaction. If they don't, then it's not a valid proposed reaction mechanism. Okay, so compounds such as N2O2 appear first on the right-hand side and then on the left-hand side. RHS, abbreviation for right-hand side, LHS, abbreviation for left-hand side. They don't appear in the overall reaction. Any complex reaction has to have at least one intermediate. Okay. The steps in which reaction occurs is called the reaction mechanism. The sum of the series of steps must equal the total reaction. I don't like to call it net reactions. Let's just get rid of that. So here's another. This is a different reaction. All right, this is a different reaction. So NO2 plus CO goes to NO plus CO2. This is a 3 here. This is a 3. So even when you might think that a reaction would just be a simple reaction like this one, bimolecular, experiment may show otherwise. And in fact, this is a 2-step reaction. So NO2 hits another NO2 to give you NO3 plus NO. So NO3 is an intermediate. Then NO3 reacts with a CO to give you NO2 and CO. So you end up with NO2 plus CO goes to NO plus CO2, which is what you have to have. In my RPIC chart, my reactants are NO2 and CO. My products are NO and CO2. My intermediate, you might have more than one. Here we just have one, NO3, and there's no catalyst. Now some people say, oh, there's a catalyst because you see an NO2 canceling with an NO2. But it has to completely cancel. There's another NO2 left over, so it is a reactant. It's not a catalyst. The intermediate does not appear in the overall reaction, neither do catalysts, by the way. Catalysts as well as intermediates do not appear in the overall reaction. Fine. Okay. Here we have decomposition of ozone, and this is an example where we have both intermediates and catalysts. We see a CLO appearing on the right and then on the left. So my reactants are O3, my products are O2. One of the intermediates is CLO. Are there other intermediates? Well, just O is formed on the product side, then comes on the reactant, so it's an intermediate. And chlorine, monatomic chlorine, is U introduced by careless use of chlorofluorocarbons and transformers or freezers, cooling systems. So chlorine's on the left-hand side, and then it comes back out on the right-hand side. And in so doing, it screws up the balance between ozone and O2 and thins the ozone layer, which is why we aren't supposed to be using freons and those kind of cooling systems anymore. There are still parts of the world that do, unfortunately. So the catalyst is Cl. So O3 is a reactant, O2 is a product, ClO and O are intermediates, and Cl is a catalyst. For example, the Cl is a catalyst, and ClO and O are intermediates. The catalyst can be identified in the mechanism by appearing on the left-hand side first, and then on the right-hand side. So hint, intermediates are produced and then used, whereas catalysts are used and then produced. Now there was another example of catalyst using HNU earlier on, and you can find that a few pages back in the book. And there's lots more examples you can find, and even look some of our videos on catalysts, you'll find more. Now speaking of catalysts, homogeneous catalysts are in the same phase as a reactant. So if I had something, let's say A aqueous plus B aqueous goes to D aqueous, then I had C aqueous as the catalyst. Sometimes catalysts are written above the reaction arrow. So if the catalyst is in the same phase as the reactants, I don't care about the product phase, but if it's in the same phase as the reactants have to be in the same phase as each other, then you're talking about homogeneous catalysis. C is a homogeneous catalyst. Okay? If, however, the catalyst is in a different phase than the reactants, then it's a heterogeneous catalyst. And one example is, let's say you have carbon monoxide gas plus NO gas. This won't be balanced. Coming out of the exhaust of your car, well, you might have platinum, palladium, rhodium, all those solids. That's your catalytic converter, these little beads, which have the property to have some sites on them stick the carbon monoxide and NO like flypaper to them, and then allow the atoms within those molecules to rearrange themselves. It provides a solid surface for adhesion of the carbon monoxide and NO to give you products, maybe like CO2 plus NO2 or something like this. At least the CO2 won't poison you like the CO will. Yes, I know CO2 is a global warming or a greenhouse gas, so that's another story altogether, which I think you've taken in some of your geography and other classes. Here I just want to focus on the fact that the phases between the reactants and the catalyst are different, and that makes it a heterogeneous catalyst. Okay, so that's an RPIC diagram. Now, in terms of reaction mechanisms, it turns out that not all the steps occur at the same rate. Some take longer than others. Sometimes you can have two of them taking way longer than the others, but we're going to simplify and just look at one step in the reaction mechanism being slower than the others. And that step is called the RDS. RDS standing for rate determining step, since that step affects the rate of the reaction more than any of the others. Imagine a sports team, let's say a volleyball team, must take a trip to another city for a game. If half the team flies, which is the fast step, and half the team takes a bus, which is the slow step, it doesn't matter how fast the flight is because the team cannot play until a bus arrives. The only way to get the whole team to the game faster is to speed up the bus trip. The bus trip is similar to the rate determining step because it has determined the time at which the team reaches the city. So there's an example of transportation. Rate determining steps, think of you driving 60 kilometers per hour down Pembina Highway. Everyone's driving at a nice pace, and then, oh no, there's construction. So that is your bottleneck, your rate determining step. And the rate of reaction depends on the concentrations of the reactants in the rate determining step. Some people use the example of a 4x100 relay race, and they say the slowest person in the relay race is the one who determines your position, and that's in the final, and that's correct, isn't it? So I would have to tell you, if everything else looks pretty equal, which one would be the rate determining step. So here we have a reaction mechanism. It's not always the first step. Sometimes it is. It doesn't have to be. In this one, in our last mechanism, suppose the first step was the slowest step, then it would be the rate determining step. And the rate of the reaction, the overall rate of the reaction, will be proportional to the concentrations of those reactants in the rate determining step. So there's an NO2 and another NO2. We're going to learn in our next lecture that the proportional symbol can be replaced by an equals proportionality constant, K times NO2 times NO2, where K is known as the rate constant. Okay. Here we have some examples to go through. We got 3 steps here, all bimolecular. And so let's get the overall reaction. Let's get an RPIC chart over here to help us. Okay, so what's happening? I like to see what the intermediates are first. I got an X and an X. So that's an intermediate. Do I have another one? R's? No. Do I have some catalysts? I don't even have any catalysts. Oh no, I got another intermediate there, Y. So that's an intermediate. So I end up with 2P plus Q plus S goes to 2T plus R. Nothing else cancels out? P's are on the same side. Yeah, that's it. So you would see that this overall reaction will be 4 bodies, and no way that 4 bodies are going to smash each other simultaneously, collide simultaneously. So rather we break it down into this series of steps. Now you don't have to memorize a series of steps. You'd be given it, then have to analyze it. So my reactants are P, Q, and S. My products are T and R, and there are no catalysts in this example. So we got the reaction, we got the intermediates, X and Y. The rate determining step is the first one. So that would mean that the rate would be K times P times Q. What would be the effect of increasing the concentration of P? Well, the rate would go up. Directly proportional. So if P doubled, everything else held constant. If P doubled, the rate would double. If P quadrupled, the rate would quadruple. Start over, what would be the effect of decreasing the concentration of Q? Well, that's a direct proportion, so rate would go down. What would be the effect of increasing the concentration of S? Well, S isn't in the rate determining step, so it's not going to affect the rate directly. I mean, you could go into start looking at all sorts of little sidebars and things like that, but to our first approximation here, it does not affect the rate. Oh, there's my answers there. What did it say? P plus Q, X plus T. What was our answer for C? Rate determining step. It's P plus Q goes to X plus T, right? Just missed that. Okay, lesson summary. What have we learned? Most reactions occur in several steps, each of which is usually bimolecular. The sum of these steps must equal the net equation. I don't want to call it net equation. I want to call it the overall equation, or just use that symbol. The mechanism for reaction can only be determined experimentally. Now, you're taking that on faith, but that is true. We'll get into that in the next lecture, that experimental trials of data get you the rate law, and from there you propose reaction mechanisms and hope that they're valid. The rate determining step is the slowest step and affects the rate of the reaction the most. Okay, so let's try some practice here. Let's write this overall reaction, and let's also have an RPIC chart here. Am I doing the answer over here? No? Okay, well, let's do it here. So R, P, I, C. Okay, so I'm going to add them together, and I'm going to get that the N2O2 is an intermediate. Are there any catalysts here? I don't think so. Oh, I have another intermediate here, N2O. First it's on the product side, then the reactant side. So that's another intermediate. So I end up with 2NO plus 2H2 goes to N2 plus 2H2O. You should always check whether that these are balanced. Nitrogen's good, hydrogen's good, oxygen's good. Yeah. Okay, so it's not four things smashing together. So there's no catalyst in this one. And we got the intermediates. I don't know what the rate determining step is. They don't tell me in that example. Okay. Next one, write the balanced net reaction and do the RPIC ones for here. So R, P, I, C. So we're going to have, let's see, what cancels out? IO minus, that's an intermediate. I minus is a catalyst. Look how I put this slopes in different directions. That's just a cool thing to do. So IO minus is an intermediate, I minus is a catalyst, H2O2 is a reactant, and H2O and O2 are products. So I end up with 2 H2O2 goes to 2 H2O plus O2. And you see that neither the the reactants are on the left, the products are on the right. Neither the intermediates nor the catalyst appear in the overall reaction. That's a similarity between them. Difference is intermediates are first seen on the right-hand side, and then later on they're on the left-hand side, and then they cancel out. Whereas, that's my favorite word, whereas catalyst you inject into the system first on the left-hand side, and then later on they come back out on the right-hand side. Okay, so let's go and try this one out here. This one does have a rate determining step. So I'm going to put reactants, products, intermediates, and catalysts. So let's see what happens here. What cancels out? An I1 cancels out and an I2 cancels out. Oh, I bet the I stands for intermediates. What do you think? I1 and I2. Do we have anything else canceling? Any catalysts? I don't think so. So we end up with P and a P. So 2P plus Q plus S goes to R plus W plus T. So that's my reaction. The overall rate of the net reaction depends on the concentrations of the reactants in the rate determining step, which in this case is the first step. So rate equals K times P times Q. Increasing P increases the rate of the reaction. That's true. Increasing Q increases the rate. That's true. Increasing S has no effect. That's true, because S is not in the rate determining step. Only changes of concentrations of reactants in the rate determining step affect the rate. Okay. Write the net reaction for this one. Intermediates cancel out. I1, so I get 2A plus B goes to 2C plus D, and the rate would be K times A times B because that is the slow step. Okay. 4, a proposed mechanism for the preparation of the poisonous liquid nitrobenzene is the following. What's the rate determining step? The rate determining step is the slowest step. So the rate would be K times C6H6 times NO2 plus. What's the net reaction? Well, to add this together, my intermediates, I got a C6H6NO2 plus. I got an HSO4 minus. Our intermediates, and H2SO4 is a catalyst. So I end up with a net reaction. You can do the RPIC diagram yourself. C6H6 plus NO2 plus goes to C6H5NO2 plus H plus. Okay. Without H2SO4, this is a slow reaction. Why? Well, H2SO4 causes a alternate reaction pathway, which must speed up the reaction because H2SO4 is a catalyst. So H2SO4 is a catalyst, and therefore it speeds up the reaction. And we'd have to look at some potential energy profiles in super detail to see how that worked exactly. Okay, so all the mathematics, introduction to rate law, we will look at that in our next lecture, which would be lecture 4. Okay, have fun. We look at all this. Hope you're learning this at a nice, steady rate.